Hi there. In this section, we are going to talk about function notation. There are a few definitions or vocabulary that we need to review, but we are going to get right into this. So the first thing, we need to define what a relation is. So a relation defines the relationship between the x values or the input and the y values or the output of ordered pairs. So I'll write that out. The definition, or a relation, defines the relationship between the x values or the input and the y values or the output of ordered pairs. So that is a relation. So there are two different types of relations that we are going to talk about. Sometimes they can simply be a set of ordered pairs. For example, relation F could be just a bunch of points. So that is one type. It could be ordered pairs. Another type is an actual rule or expression. So a rule or expression, such as, and I'm just going to make this up, g of x is equal to x plus 1. So that there are two types. They can either be ordered pairs or an actual rule or expression. So more vocabulary. The domain is a word that we're going to hear a lot. That is the set of inputs or x values. X's, or the independent variable. Independent variable. We also have the range, which is the set of outputs, y's, or dependent variable. So the set of output, y's, or dependent variable. Now we finally get to function and its definition. Oh goodness, my pencil's falling apart. Here we go. So the definition of a function. And so much of what you're going to learn in Math 171 is all about functions. So this is kind of getting right to the grit of what you're going to do in 171. So a function is a special type of relation that assigns one output to every input. So a function is a special relation that assigns one output for every input. There is exactly one y for every x. So what does a function look like? How can we show that a relation is a function? There are a couple ways. We can use mapping. You probably saw this, where let's just make up some x's. So we've got these x's and these y's. If it is a function, every x has exactly one y, or every input has exactly one output. This is a function. However, if you have, and I'm just making up numbers, if you have something like this, where you've got the ordered pair 2, 4, and 2, 5, this input has two outputs. So this is not a function. It's a relation, so you can graph it, but it is not a function, which is a special type of relation. So another way you can check to see if it's a function is by using the vertical line test or the pencil test. So if you graph, or if you look at graphs, and you take your pencil, or let me shift my paper up a little bit, and you put your pencil in a vertical direction, and you go from left to right, that graph, meaning not the x and y axis, that's not included in what we call graph. If you go from left to right, that graph can only touch your pencil one time at any moment. So this is definitely a function. A line is absolutely a function. We have a parabola. Now this is a pretty bad graph, but we're going to assume it is an actual parabola. If I go from left to right, my parabola does not touch my pencil more than once at any time. Now, if we have a parabola in this direction, look at this. Here's my vertical line, and it is touching the graph twice. It is a relation, but it is not a function. So this is how we use the vertical line test. Now, we also have function notation, which is getting to what we actually are going to talk about today. So function notation is just another way of writing a function. It's a shorthand of sorts. So if we write the equation y equals x squared, just as a reminder, x squared is a quadratic, and that would make a parabola, something kind of like this, but not oriented or not shifted exactly like that. So this is absolutely a function. In function notation, we would write f of x is equal to x squared, and that is read f of x is equal to x squared. So we call that shorthand. Doesn't appear as shorthand currently, but it is absolutely mathematician shorthand. So let's look more at function notation. If we've got f of x, the input variable is our x. Whatever it equals is the output variable, or the output. So whatever it equals, this answer, that is our y, or our output. So let's look at this first example, and we are on page 33 in your workbook. It says, interpret this. Now we read this as f of negative 2 is equal to 8. So what this says is, in this function, negative 2 is an input. Here is my x. It is the input to the function f. When the input is negative 2, the output, or my y, is 8. We can also say that the point negative 2, 8 lies on the graph. I'm going to write all that down because I know sometimes it's hard to catch it all. So, there are 3 points to consider, 3 things to note. Negative 2 is an input to the function f. That's one thing that statement tells us. Another thing is when negative 2 is an input, that doesn't look very good, input to the function f, the output is 8. Finally, the third detail that statement tells us is that the ordered pair -2, 8, remember our ordered pairs, the x comes first and then our y, and in our function we've got our x and we've got our y, lies on the graph F. So those are 3 details that we can glean from this statement. F of -2 is equal to 8. One other thing I wanted to mention about function notation. So a lot of times when we're evaluating expressions, we see parentheses and we think multiplication. In function notation, these parentheses do not mean multiplication. Absolutely not. That is not implied multiplication. This is just part of our shorthand that we use parentheses, but that does not mean that you do any type of multiplication in this case. So I just wanted to point that out. So before we move on to the examples, I also wanted to remind you about the order of operations. Now, we all learned our own acronym or catchy phrase to help us remember the order of operations. I remember PEMDAS. But there are a couple of extra things we have to remember. So in PEMDAS, we have to simplify inside the parentheses first. Simplify inside the parentheses first. Now, inside of your parentheses, you also have to use your order of operations. So if you've got multiple operations inside of your parentheses, you have to use order of operations inside of your parentheses first and then continue outside of your parentheses. So the E, when you're in regular Algebra 1, it just means exponents. But when you get a little bit fancier in pre-calculus, you need to remember that it is absolute value and exponents. There's my cuckoo clock. All right, M and D, they go together. So we have to remember that this is multiplication and division in the order that you see them from left to right. So you may do division first. It just depends on what comes first. So multiplication and division from left to right. So again, that doesn't mean you always multiply first. If you read it from left to right and you have a division operation, you do that first. So it's multiplication and division in order from left to right. And the same is true about addition and subtraction. Addition and subtraction from left to right. All right, so let's get to the examples. If the ordered pair 5, 1 is on the graph of G, evaluate G of 5. Now remember, this 5 is our x. That's our input. So it wants to know what is y when x is 5. What is y when x is 5? Well, it's already told you. It's given you the ordered pair. When x is 5, y is 1. So G of 5 is 1, and 1 is your answer. When x is 5, y is 1. All right, number 2, given f of t is equal to t plus 5, evaluate f of -1 and f of 0. So we've got to do two things. We need to know what is y when x is negative 1, and what is y when x is 0. So the first thing we're going to do is we're going to evaluate not x, t. It should have been a t. T. All right, so we're going to first evaluate when t is negative 1, which means we're going to substitute negative 1 every time we have a t. Instead of t plus 5, it'll be negative 1 plus 5. And we simplify. Negative 1 plus 5 is 4. So f of negative 1 is 4. And that also correlates or translates to the point negative 1, 4. Our independent variable is negative 1. Our dependent is 4. And we just get to do it again. F of 0 is, instead of t plus 5, we're going to put 0 plus 5. So f of 0 is 5, which means that another solution is 0 and 5. All right, let me get this scooted up a little bit. Evaluate the function g of x is equal to negative x squared minus 5x plus 1 for x is equal to 4, negative 1, and negative 4. So we get to do this 3 times. All right, so the first one, g of x, we're going to use g of 4. We're going to substitute 4 in for x. So g of 4 is equal to negative 4 squared minus 5 times 4 plus 1. So I've substituted 4 in for x here, and negative 5x or minus 5x means 5 times x, so I indicated it that way, plus 1. Now we have to be careful right here. This x is being squared first before we make it negative. So we have to be super, super careful. This is going to be negative 16 minus, we do exponents first, then we multiply. 5 times 4 is 20, plus 1. Now we do addition and subtraction in order from left to right. Negative 16 minus 20. My pencil just ran out of lead. Negative 16 minus 20 is negative 36. Plus 1 is negative 35. So g of 4 is negative 35. Now we get to do this 2 more times. G of negative 1. We're going to substitute negative 1 in for every x. So we've got negative 1 squared minus 5 times negative 1 plus 1. We are going to flex our negative muscles. So now we've got negative. Now, negative 1 squared is the same as negative 1 times negative 1, which is a positive 1. So we've got negative 1. Here we've got negative 5 times negative 1. That gives us a positive 5 plus 1. Negative 1 plus 5 is 4, plus 1 is positive 5. Finally, g of negative 4. So we've got negative 4 squared minus 5 times negative 4 plus 1. We get to do this all again. Negative 4 squared is negative 4 times negative 4, which is positive 16. So we've got that negative just comes right down. Negative times positive 16. A negative 5 times negative 4 is positive 20 plus 1. Oh my goodness. You see what's happening here? That's where our parabola is looping back around. All right, negative 16. No, just kidding. It is not looping back around. That was a lie. Negative 16 plus 20 is 4. oh yes, plus 1 is equal to 5. It does loop around, but I was confused. All right, so we've got those 3 answers. When x is 4, y is negative 35. When x is negative 1, y is 5. And when x is negative 4, y is also 5. So that graph looks something, oh goodness. I'm gonna have to get, oh, here we go. That graph looks something, this is just gonna be awful. Like this, I believe. So here and here. Anyway, horrible sketch. All right, 2 more examples. We've got an absolute value function. So we substitute in exactly the same way. F of 1 is equal to the absolute value of 1 minus 4. All right, we simplify inside of the absolute value sign first. So 1 minus 4 is negative 3. Remember, the absolute value is the distance from 0. So if we look at our number line, negative 3 is 3 spaces away from 0. So the absolute value of negative 3 is positive 3. All right, f of 4 is equal to the absolute value of 4 minus 4. The absolute value of 0 is 0. And finally, f of 7 is equal to the absolute value of 7 minus 4, which is the absolute value of positive 3, which is 3. And we will look later, absolute value looks like a V, like this. We will look at these graphs in a little bit. All right, last example. A baseball player throws the ball from the outfield to home plate. The height of the ball in feet above the ground, t seconds after being thrown, is represented by the following function. H of t is equal to negative 16t squared plus 60t plus 6. Determine and interpret its meaning in the context of the problem. So let's figure out what our variables are. So we've got h of t, which is, what are we calculating? What is it that we need to know? Because we know that t is the time in seconds. So we are using the time in seconds to help us calculate h of t, which is the height of the ball after t seconds. So we're going to use time as our input variable to help us calculate the height. And just for a bonus, if we were to evaluate h of 0, that is the time at 0 seconds, that would be the starting height of the ball. So where it is at the very beginning of the experience. So that concludes the notes section of function notation. If you could please flip over to page 35, there are several function notation practice questions.